few minutes out before class starts. Let's see here. 11:26. Yeah, we got a couple minutes. Time for me to fiddle with my computer and my camera. I wanted to know if any of the video participants out there were having trouble submitting work. I got 2 emails from 2 different students saying that it was difficult for them to submit work on Blackboard. Have you had a problem like that, Riker?
No.
I did at the beginning, but now it's not because it wasn't a session for me to submit it.
What do you mean there wasn't a session?
It just wouldn't. I don't know why. It just wouldn't at the first class. It wouldn't let me. So that's why I emailed you the first homework in the first lab.
Oh, you emailed me the first homework in lab? Shoot, this is getting really confusing for me because I've got emails coming in from all over the place. Hey, and oh, Juju's here. Holy smokes. Hey, Juju. Welcome to class, buddy. You gotta unmute your audio for a sec for me to hear you.
I'm trying to like put the volume up.
Oh, there you are. Okay. Hold on, Bella. That's troubling for me because I don't. Bella, at the end of class, try to remind me that I need to search my emails for your submission. Because what eventually changed? What, like I had the homework in the lab set up so you could submit something, and other people were submitting things. So
yeah, I don't know. Actually, Blackboard
I cannot hear this teacher right now. What's good? The volume.
The Blackboard was giving me trouble with other teachers as well, so it just most likely been on my end of the thing. Because I couldn't, like, one of the teacher kept
Can you guys hear me?
I can hear you, Juju. Yeah.
Oh, okay. All right.
Loud and clear. Welcome to class, buddy. It's nice to see you.
I know. I had to figure out. I had to set, like the whole like computer situation was. I had to figure that out, but now I'm alive.
Good. And it's fun to meet up all here in virtual space. Hey, are you keeping up with the submissions, Juju?
Yeah, I have to go back on the on my Gmail and look at the stuff that I missed so I could start doing the labs and stuff.
All the labs, all the homework sessions, and all the lectures are all on my YouTube page, and you can get them all directly embedded in Blackboard. But you should try to catch up on that because I'm worried it's going to be like a snowball avalanche where like if the backlog builds up in a few weeks, you're not going to be able to like keep up with it. So do that. You got work to do for me this weekend, okay, Juju?
Okay, yeah. I don't even know where else to go.
All right, exactly. You guys are just like shooting fish in a barrel here, you know?
Yeah. So yeah, all right. So it's all on I can log on to the Blackboard and all of them will be right there and I could just submit it.
Yep, you can submit them all on Blackboard. Here, I'll share my screen with you. The way that it's supposed to look, if you're seeing my screen, Juju, is you go into Blackboard, right? And there's a little tab over here for homework, and there's a little tab for lab. So like, for instance, we did lenses and telescopes this week, lab 7. You can download the sheet right there. And then if you go to the announcements, I just kind of put I put all the labs and lectures on announcements. So there's your lenses and telescopes lab. You can click on it there. Also, I have a YouTube page. It's easier for you guys to use YouTube if you're having trouble with Blackboard. Let's see here. If I go to my YouTube, what the hell? I'm still kind of new to my own YouTube, so I don't know how to go. I mean, I use YouTube all the time, but now I'm like a content creator and your channel. There we go. Okay, so this should be my YouTube channel. I'll put it into the chat log here in class.
I'll subscribe and like everything.
Subscribe, like, comment, whatever you.
Yo, you got my
these days. Okay, hold on. Where's
follow the Instagram? No,
yo, shout me out.
Hold on. Let me stop share.
How did you just do that?
I'm a wizard. I'm a wizard of.
You just took over my computer screen like that. Wait.
Okay, I put my YouTube channel. Hey, Ellis, how you doing?
Well, I can do this on my iPhone.
Huh?
Yeah, I'm on my iPhone right now.
I can like be on Zoom on my iPhone.
Yeah, you
Nigga,
can.
see, it's fucking alive. Bro, I didn't even know I could do that.
You can do
What?
so many good things. Hello, Mike.
Daniel.
I didn't know.
Hey, how's it
Wow.
I want to like wave to different people depending on which little box you're in. So it feels like class. Okay, so today we're going to do the interior of the sun. We're going to do a homework session today on chapter 15. God knows how I'm going to cover all that, but it's not very hard, so that shouldn't take too long. Give me just 2 minutes here just to finish combobulating myself before we start, okay?
Lady.
Hey, Juju, the etiquette is to mute yourself until you have something to say to the class, okay?
Oh, see, all right, now I'm okay. See, I'm learning.
Just hit mute, and then if you want to talk to us, unmute to talk to us. That cuts down on the background chatter.
Did you hear about all the Zoom hacks?
Here.
Yeah, you mean like Zoom bombing, Morgan?
Yeah, people are getting the username and password for the Zoom lessons and then they're joining them.
Yeah, I read about that in the, I don't know if it was the Washington Post or the New York Times, but people are Zoom bombing. They're like hacking into Zoom lectures and like showing people, you know, whatever horrible things they can find on the internet, like ghosts. So my buddy Zaz, who's hanging out there in the background somewhere, he was telling me today that Zoom's a pretty terrible video chat service to use because if you install their program, as I foolishly did, it's basically like one step away from malware. They collect your data, they send it to Facebook, they do all this stuff. So he suggested a couple other video chat options.
I'm here.
Oh, hey Zaz, yeah. So you're saying it's
I'm here. It's totally true. It's the most awful thing ever. I mean, you know, from the dark patterns when you try to run it in the browser and it forces you to download the application anyway, all the way through that, like it was installing servers. Like the only piece of software that's like supposedly legitimate software that Apple's malware system like shut down last year was Zoom because they were installing this hidden web browser, web server that would allow any remote person to connect and activate your webcam without you knowing.
Oh, that's crazy. You can activate your webcam without you knowing it?
Hello.
Yeah.
Oh my gosh.
It's just a total security shit show.
Yeah, so until I find, Zaz has recommended a few other video services I'm going to look into, but you might want to put tape over your camera.
Hello.
That's what I do. I told you, I can't let the people spy on you, you know?
Of course, if you have a laptop, just close that.
Virus. Now we have this virus. Like, what's up with this? But ting.
A lot of bad things going around there. One thing I really do like about Zoom, however, so I'm going to have to ask Zaz if any of these other programs have it. It's really critical for me to have the share iPhone feature because then I can turn my iPhone into a little remote camera so I can show you guys laboratory measurements and things. I make use of that feature every day. It's so critical. So I hope that some of these other programs you're suggesting have such a feature.
Yeah, I don't know about that. I can look into it, but yeah, that's not something that was on my radar.
Okay, yeah. Well, anyways, we got times to think about that and talk about it. Oh my gosh, it's just 11:34. Look how time flies when I'm hanging out with all you guys. Let me roll my tape, and then after we roll the tape, we'll get to it. I'm on astronomy. Britain's Wacky Universe. Open with VLC. Okay, there we go. And okay, any last? Let me see here. I'll magnify this. Any last comments before we get going here? Everyone good? Okay, so last time I didn't play the intro, and I got some flack for it. So you asked for it. You're getting it. Here you go.
Hello.
Hello, space fans, and welcome to Professor Britton's Wacky Universe. Okay, we're back. Now listen, I've been threatening this dangerous radioactive demo for like 3 classes now, and we haven't gotten it. But today we're going to actually descend into the bowels of the sun, into the very heart of its nuclear core, and we're going to do a little lecture on nuclear physics. One of the first of many, actually, because of course in Astronomy 1020, we're going to learn to compare the interior fusion cycles of many different types of stars. And we're going to start by going in detail into the sun's nuclear reaction sequence, because that's going to be our first training ground for nuclear physics. And it also includes a demo somewhere, which I have not prepared. I have a rock of radioactive uranium that I would like to share with you at some point. It's called carnotite. And somewhere around here, I have a Geiger counter, which we can use to measure radioactivity. We can find out just how radioactive Professor Britton's apartment is after years of doing bad things in here. So anyways, we've got a Geiger counter. We've got our radioactive rock. You guys can see the screen. I believe we're recording here. That's good. And let's go into lock speaker mode so that the people watching at home can see my screen. So if this is your first class, like Juju, if this is the first time you're with us, you can go between gallery mode to see all your friends and speaker mode to see me. And if you double click my box, it'll lock on my screen so that you guys can take some good notes. Okay, now, if I remember what we were doing last time, we ended our class discussing the 3 interior layers of the sun.
Yep, the convection zone, the radiation zone, and the core.
Yes, sir. Hold on, let me get the autofocus in here. Let me share that screen one more time. And let's go ahead and let's find the 2 lecture slides that I think we're going to want today. We're going to want our lecture slide on the sun, which is available on Blackboard. You can download it to your personal terminal. And we're also going to need the light and telescopes lecture in case we want to compare regimes of the electromagnetic spectrum and whatnot. So I've got a nice little picture here of the interior layers of the sun, or basically all of the layers of the sun, on slide 29, function F529. And of course, I think we've all decided that we don't feel like doing a final exam this year with all of this virtual online bullshit that we're going through. But if we were to do a final exam, I would certainly be testing you on these layers of the sun. So let's pretend like it really matters here. And once we go below the photosphere of the sun, that so-called virtual surface layer, the surface layer of light, the gas becomes too thick for photons to wiggle their way out through the pea soup. And that means we don't actually get to directly observe these layers, the convection zone, the radiation zone, and where we want to end up quickly, the heart of the sun, the nuclear core. Now, you could rightly ask me, well, how do we know what these layers are if we don't have the ability to see directly into them? And the answer is twofold, or maybe threefold. The first is when the Solar Dynamics Observatory studies the surface of the sun. So let's go over here to, for instance, to YouTube, and we'll go back to that thermonuclear art video, which I love so much. Remember that the Solar Dynamics Observatory is constantly imaging the sun at a variety of different wavelengths here. Let's kill the sound. And when we stare at the surface of the sun, we can actually measure oscillations. They're basically like earthquakes on the sun. They call them sunquakes. And these oscillations on the sun allow theoretical physicists to model the interior layers of the star. So basically it's done through computer modeling, but the data that they input into the model are the oscillations of sunquakes they see at the surface. So another way that we can learn a little bit about the interior of the sun directly is because although photons are not capable, function F529, sorry, I'm a terrible multitasker. Although photons and light cannot escape the interior layers of the star, there are nuclear reactions inside the sun which emit tiny particles called neutrinos. That's something I'd like to talk about today. And neutrinos are so microscopic that they can fly through the dense matter of the sun as if it was transparent glass. And we can detect these neutrinos, and that helps us study the rate of nuclear reactions. And if you put that together with models of the sunquakes, it's, you know, it's a little bit of deductive science, but, or I guess inductive science maybe, but you can sort of figure out these three different, that the sun has broadly three different layers that we'd like to talk about. The convection zone makes up maybe a third of the sun's radius. The radiation zone, something under 2/3 of the sun's radius. And the inner core is somewhere between 10% to 15%, depending on which model you look at. Now, let's see if you guys remember anything from our previous lecture. This was a subtle point that might have gotten lost at the end of the class because we were getting tired. But if we were to compare the convection zone of the sun to the radiation zone, what would be the big difference? Does anyone out there think they understood my lecture enough to answer that question? The sun doesn't think of itself as having layers. The sun is a ball of gas and plasma that, as you descend from the exterior to the interior, gets hotter, gets denser, and becomes more ionized into a pure plasma of protons and electrons. The sun doesn't really think of itself as having layers. We impose the idea of layers on the sun based on how energy is transported through these layers. So what do you guys think? Differences between the convection zone and the radiation zone? I don't expect you to know the answer to this, but I thought maybe you could try, or maybe someone gets it.
One's hotter.
Okay, one's hotter, so let's write down their temperatures, right? In the convection zone, the temperatures are getting higher and higher as you descend into the sun. But if you wanted to take an average temperature over these huge regions, you might say something like 100,000 Kelvin in the middle of the convection zone, but the radiation zone at least goes up to somewhere between 1 to, well, let's not say 10 million Kelvin, because that's getting up to nuclear fusion territory. Let's say 1 million Kelvin.
Yeah.
Hold on, class. I lost my bloody eraser. Huh. Okay, paper towels it is. Hold on. Can't find my eraser. Okay, I must have dropped that little puppy the other day, but this will have to do.
Isn't one layer fully ionized plasma and the other one is just semi, or am I thinking?
Yeah, this is actually a big point. So the convection zone is a mix of gas and plasma, all right? Whereas the radiation zone is a fully ionized plasma. At these temperatures, no neutral gas is remaining. Okay, Nathan, if that was your voice that I heard.
No, it was Marcus.
Oh, I'm sorry, Marcus. Marcus, I apologize. So Marcus, while we're talking here, what does that mean for energy transport?
Well, in the convection zone, because it's gas and plasma, it would be transferred in convection zones.
Yeah, or in convection cells, maybe.
Yeah. And the other one, I'm not 100% sure.
What are your three modes of energy transport? Do you remember that?
Convection, conduction, and I'm drawing a blank on the last one. Swimming.
Anyone? Can anyone help? What's that, Riker?
I got nothing for this one.
Oh, man. Come on, someone knows the third mode of energy transport, right? I thought you were all enlightened.
I don't know when we're in trouble.
How does energy get from the sun to Earth?
Is it
Oh,
radiation?
oh, it's the wavelength.
Radiation.
Radiation. Thank you.
Oh,
So, Marcus, what mode of energy transport do you think is taking place here in the radiation zone?
Radiation.
That's right. All right. Now, to start off our class today, I want to explain why. What makes the sun decide to go from radiation to convection? Learning the answer to that question is actually going to give us a lot of intuition about stars as we go forward. The rest of our class, students, with a cool exception of a lecture on relativity, is learning more than you ever wanted to know about stars. And stars are actually difficult things to build up intuition about because they don't behave like matter does here on our terrestrial laboratory on Earth, where we stay mostly at sea pressure and at very mild ranges of temperatures. A star is a massive sphere of gas. It's being squeezed by gravity, and there's a lot of complex things going on. Let's take a look at my slideshow again so we can talk about why the sun is transporting energy here by radiation versus here by convection. And so let's see if we can find the slides that explain the difference between the two. So you'll remember, here's my picture 46 of how convection works. Convection works by hot bubbles of gas rising and expanding, displacing cooler bubbles of gas that sink, and they set up a convection cell. And the words that I used last time is that convection moves matter by bulk transport. You're moving giant blobs which contain zillions upon zillions of atoms, or in the case of air, molecules. Whereas conduction is atom to atom jiggling, that's direct jiggling between atoms. Conduction doesn't really happen inside the sun because conduction usually takes place when you're transmitting heat across solids. That's not always true, but it's probably the best way to start by thinking about it. So if you cook a pork chop on the frying pan, your frying pan has jiggling molecules or jiggling atoms of iron or some kind of metal, and they're heating up the pork chop by direct atom to atom jiggling. Conduction works well transmitting energy through solids. And of course, some gases. If you cook a turkey in your oven in Thanksgiving, it's probably cooking it mostly through conduction between air and the turkey, unless you have got a fancy convection oven. When we get to the radiation zone, our star is a fully ionized plasma. Now, do you guys remember what the composition of the sun is from our previous lectures? What's the composition of the sun?
Helium, hydrogen, and then other metals.
70% helium, 28%.
70% helium?
I meant, sorry, 70% hydrogen, 28% helium, 2% heavier metals.
And what's a hydrogen atom look like, Marcus?
It is 1 proton and 1 electron.
So if I were to ionize that atom, oh, there's my eraser. If I were to ionize that atom, what would it look like?
It's just 1 proton, correct?
Well, aren't you forgetting something? What
And a
happens to the
neutron.
electron?
Oh, and the neutron.
No, neutrons. We ain't talking. The ratio of deuterium to protium is very, very low. So forget about neutrons. There ain't no neutrons in your typical hydrogen atom.
My bad.
If you know what the composition of a hydrogen atom is, what do you get if you ionize it?
If you ionize it, you're losing the electron.
So it's just the
Okay,
proton.
I think you guys have been talking to chemistry teachers too long. In chemistry, when you lose the electron just disappears from the space-time continuum and is gone. But the electron does not just fly away into outer space, leaving the sun. It's still fucking there. It's just not bound in an orbit to the proton, right? The electron does not disappear. So here's your proton, and when you ionize it, the electron is, guess what? It's right there. It hasn't really gone anywhere. It's just that its kinetic energy is too high for it to remain in a bound orbit. In other words, in the radiation zone where we have a fully ionized plasma, you basically have a sea. One of these red markers is going to work for me, I know it. You have a sea of protons, there we go, okay? And you also have a sea of free electrons floating around. And the radiation zone is in some cases like a giant pinball machine. Now look, yes, there are some ionized helium atoms there. There might be some alpha particles. Hey, do you guys remember what an alpha particle is? What's an alpha particle? One of the 3 types of radiation discovered by Madame Curie.
Helium nucleus.
All right, so explain to me what that looks like, Riker.
That should be,
particle.
that's 2 protons
Anything else?
and 2 neutrons.
Fine. Okay. So there's probably a few alpha particles floating around in the soup there as well, right? There's one other component that we need. By the way, this is inside the radiation zone, right? This is where temperatures are close to 1,000,000 Kelvin. We're missing one last component here. What else do I need?
There we go. You definitely go. Let's go.
Gamma rays?
That's just like literally like. Let's see.
No one knows. Hey, Juju, mute yourself.
Is it the photons?
Gamma rays?
Yes. Who said that? I didn't expect you to get this. Who said that?
Tim.
Tim, thank you so much. We need some photons in there because we've got a gas plasma thing that's at 1,000,000 Kelvin, right? This shit is hot and it's going to be glowing. In fact, not only would there just be photons naturally from a gas at this temperature, but also remember you're sitting on top of a big nuclear bomb that is emitting gamma rays. And those gamma rays are radiating up from below. Let's use purple, symbolic purple, to represent my short wavelength, high energy gamma rays. And I'm going to send them through the pinball machine here, okay? So here comes the gamma ray, bump, 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 bump. And my gamma rays, all my gamma ray photons are ricocheting off these particles as it makes its journey through the sun. What do you think a gamma ray is most likely to bump into? An alpha particle, a proton, or an electron? If you had to guess.
Electron.
That's actually correct. The electron is the electron. I did not expect you to say that. The electron is the smallest particle of all of these, at least in terms of its whatever radius. So, although remember, these particles are not so particle-like. They don't actually act like little BBs when you look at them up close. In any case, the probability of how do I say this? The chance of a photon hitting one of these particles does not depend on its physical radius, but it depends on something called the quantum mechanical cross-section. It's got something to do with the interactivity between the particle and the photon. And actually, the photons, the gamma rays, like to bounce off of the electrons more than anything else. The free-floating electrons have the highest cross-sectional interaction between photons. Now, as these particles go ricocheting their way through the plasma soup, remember, these are not, you can't capture the photons very easily because normally it's neutral gas that likes to capture photons. So the photons kind of bounce off these things. And during their collisions, you'll have a situation, I'll draw it up here with this electron. Here comes a very short wavelength, high energy gamma ray, okay? And it's going to collide with this free electron. And when it does, the electron is actually going to get a little kick, just like you punched it. And it's going to increase its kinetic energy and kind of heat up the surrounding gas. And the photon will ricochet off the electron and lose some of its energy. And in the process, as it loses its energy, it will increase its wavelength. Now, I'm going to say something that's not true, that's cartoony, just to make some sense to you guys. But let's imagine that it was a really short wavelength gamma ray, and it slammed into this electron so hard that it comes out as a longer wavelength X-ray. It's probably actually not that extreme. They're probably just much smaller changes in wavelength. But it's happening so many billions of times per second that over time, these photons can change their wavelength and create a whole field of radiation across the electromagnetic spectrum. Now, the process by which the photons scatter and ricochet off of free particles is what's known in physics as a random walk. A random walk is a statistical concept where photons bash off of free plasma particles and slowly but surely wiggle their way from the interior of the sun out to the surface. Just because I'm in a frisky mood today, I'm going to tell you guys the story of a random walk because it may show up in other parts of our class. Now, the story of a random walk it begins, like many of our favorite stories, at the bar, okay? And so here we have a bar, and stepping out from the bar is a drunk dude. Here he is. He's got a can of Heineken or something. And this guy is so drunk that there's a 50% chance that he will take one step to the right and a 50% chance that he will take one step to the left, okay? Now, the man is going to attempt to stumble somewhere away from the bar. And let's say that 1, 2, 3, 4, 5 paces away is his home, okay? So here's home. And let's say 5 paces in the other direction, 1, 2, 3, 4, 5 is jail, okay? And over time, this man is going to stumble himself 1 step to the right, 2 steps to the left, in an attempt to end up at one of these 2 locations. This is actually called a one-dimensional random walk because our drunk person can only take a step to the left or the right and move back and forth along the number line. Now, we can't predict with any certainty whether the bum will end up at home or whether he'll end up in jail because it's sort of like a coin toss which direction he ends up moving towards. But one thing's for certain, as the drunk man takes steps, he is going to begin to wander further and further away from the bar in a process called diffusion. Diffusion could be thought of as the slow leak of light from a star. Because remember, the man here represents the gamma ray photon wiggling his way through the plasma soup. Okay, now the man takes 1 step to the right, 2 steps to the left. 1 step to the right, 2 steps to the left. And over time, diffusion will slowly drift this man towards either home or jail. While we can't predict which place he will end up, we can model the situation using the binomial theorem, the same theorem that lets you cheat at dice or cards. And you can calculate in a more advanced class that the number of steps that the bum will need to take is the square of the distance that he intends on traveling. So how many steps will it take the bum to get home?
25.
That's right. Now, this was a simple case of a one-dimensional random walk. Now let's look at a little cheap illustration I have in my PowerPoint slideshow.
If you wanted to, could you do a I guess a experiment or demonstration by using a coin since it's a 50-50 thing?
You certainly could, my friend, and people do it all the time. Studying probability is an important stepping stone to understanding statistics. And it's also cool because it just, I don't know, it teaches you useful things in life that come up from place to place. So it's worthwhile to take some time to study your permutations and combinations, and flipping coins is a nice way to do that.
Yeah, Frank.
I want to show you guys something here. I want to show you.
What was that you said?
I was calling you out on our math class where we're doing probability and permutations right now.
Oh, are you doing that in the virtual space?
Yeah,
Yeah.
we are.
Oh, cool. So you guys then know the formulas for combinations and permutations, right?
Yes.
Yeah.
Wait,
All right.
are you in math for
Well,
liberal arts students?
I'll be
I don't know if
calling on you
Frank
guys
knows.
extra then, okay? I'll be calling on you guys extra.
Thanks,
That's right.
Riker. Yeah, thanks a lot.
Hey,
Oh no, I'm gonna actually make you work in class. Come on now, Frank.
Hey, I've been working.
actually, I was always really bad at calculating combinations and permutations. I only learned
Yeah,
them
I don't
in
understand what we're learning in that class. I don't understand the whole like truth tables, this and that, ABC 1, 2, 3. Like, what is
Look,
this?
you gotta,
Yeah,
you
it's
gotta try
not
to,
math.
No.
you need to
got
try to
my-
find a sinister motivation to excite you about this stuff. Just remember, if you get really good, you can take yourself down to, you know, your local poker parlor or something and sort of calculate the probabilities of pulling queens and aces and cheat your friends in cards. You know, this is
See,
a
here's the thing.
motivation to learn math.
Here's the thing. I already play Magic the Gathering and I play D&D, so I'm rolling dice and playing with cards regularly,
Well, then that should give you some insight into your chances of winning.
which is why I have my insight.
Anyways, I want you guys to look at this picture I have. This is a computer simulation of a 3-dimensional random walk. I don't know how many steps this is. Maybe it's like 1,000 steps or so. And let's imagine that each one of these jagged lines here is what is called the mean free path. That's how far a photon will travel before it bumps into a free electron. My gamma ray starts over here, which might be near the core of the star. And my gamma ray might want, oh, I can draw on this thing, can't I? Let's annotate. Let's draw with a line. Ooh, check this out. Oh, thanks. The gamma ray will start here, and it wants to end up somewhere over there. Maybe I should change my color to red. But its journey is not this straight line that you see here in red from point A to point B. It's taking a meandering journey. Okay, this was cute, but how do I get out of this? It's taking a meandering journey where in the process of going from the core to the surface of the star, it's going through zillions upon zillions of ricochets in a chaotic journey around the sun before it can get to its final destination. Now, let me tell you a statistic that I think is pretty remarkable about this. The photon makes so many ricochets and so many collisions in its journey throughout the star that a typical time scale for one photon to leave the star, right? So if you have one single gamma ray photon, the time it takes to get from the core of the sun to the surface at the photosphere, so the time to go from core to photosphere is a typical time scale of 1 million years. That's 1 million years for a single particle of light to get from the core of the star to the surface. And think about why that's so wacky. I mean, how long does it take photons to get from the photosphere to your face? 8 minutes. So every time you're drinking a pina colada there on the beach on a sunny afternoon, the photons that are tickling your face had an 8-minute journey from the photosphere to your face through outer space, 1 astronomical unit away. But they had a 1 million year journey trying to wiggle themselves through the pea soup of the star. And there's another concept that's kind of crazy about this too. If tomorrow, if nuclear fusion were to stop in the center of the sun tomorrow, the sun would continue to shine at approximately 4 times 10 to the 26 watts for another 1 million years as light slowly continued to leak its way through the body of the star.
But it could have stopped
sure hope
1
that
million
happens.
years ago.
Well, right, but we're capable of calculating the rate of nuclear fusion inside the star because we measure neutrinos from it. We're going to get to that in just a moment in the next part of our lecture. So we're not confused about the age of the sun, at least to 1 or 2 significant figures. We have a vague idea that the sun is about 5 billion years old and it's got another 5 billion years to go. We actually did that calculation last week. Do you guys remember that?
Yes.
We did that calculation. So it's even doable at the 101, at the astronomy 1010 level.
Yeah.
Okay, so here comes the big question. The question that I was trying to get around to, although I was certainly taking my time as usual. If the photons like bouncing off of these plasma particles, right? And they like to ricochet their way through the plasma of the sun, why do they suddenly stop? And why do the photons stop transmitting energy and suddenly the star switches over to convective bubbles when you get to this point in the interior of the star? Anyone think they can guess why?
Is it because of the, I forget what the term is, but it's the balance between the gravity and the fusion or fission?
That term is hydrostatic equilibrium, and not exactly.
Yeah.
Is that Nathan or is that Mark?
Yeah, it's Nate.
Nathan, okay. No, it's not exactly. Hydrostatic equilibrium is happening all throughout the star, but it's something to do with the particles themselves.
Would it be because the chromosphere is so much, the
No,
convection zone
don't
is
say
so much,
chromosphere.
I
Convection.
know, because the convection zone is so much cooler than the radiation zone.
Okay, but it's not that the temperature is related to this problem. But what's different about the gas here versus here?
One is gas and plasma.
That's the answer.
One is this what's the word? What's that word? Diffusion.
Well, diffusion's happening all throughout the radiation zone. But let's take a look. It's the ratio of gas to plasma that switches it over. So before you get to the convection zone, right? All you have are a bunch of free ionized particles, and you have the photons scattering their way through the mix, right? Plasma particles cannot absorb photons. But as soon as you hit this temperature layer, where it switches over to maybe 100,000 Kelvin and you start increasing your, I'm going to tell you something really stupid, something that's not true, but maybe is better for you, okay? So here it's all plasma, okay? And here it's all gas. This is a lie. And I'm just going to tell you this lie because maybe it's more helpful for you, okay? So imagine we're going to suddenly hit a wall of neutral gas in which all of the electrons were now bound to the protons, okay? Atoms of neutral gas can absorb photons. And these photons, when they hit the wall of neutral gas, it's like they're hitting this brick wall where suddenly the gas becomes opaque and all the photons start to get absorbed by the atoms themselves. This causes the gas to heat up in pockets, in bubbles, where they're collecting too much energy faster than their surroundings, and so they become sort of like a hot air balloon. Here you have a hot expanding bubble, or a hot expanding pocket, that's gaining energy from gamma rays below faster than conduction can sort of transmit it to its surrounding areas. And the result is these bubbles begin to rise, and the cooler bubbles above begin to sink back down, setting up a convection cell. Now, suppose you were a pesky student, a really pesky student, and you had paid close attention to my earlier lectures on absorption and emission in atoms.
Riker.
Yeah,
A little
Riker.
called out, but I'll take it.
All right. You might remember that the spectrum of hydrogen is pretty minimal, right? And the sun is mostly hydrogen gas to a first approximation. This is a picture of the emission line spectrum of hydrogen, showing you that hydrogen is capable in the visible spectrum of producing 1, 2, 3, okay, maybe 4 or 5 different emission lines. And that means that if photons come into your hydrogen atom, they are capable of absorbing 1, 2, 3, 4 photons. And a pesky student might say, hey, bro, if we're talking about hydrogen gas is really only capable of absorbing maybe one red photon called hydrogen alpha, one blue photon called hydrogen beta, and one purple photon called hydrogen gamma. What about all these other photons that are trying to wiggle their way through the star? Won't they pass through the hydrogen atom like it was transparent glass? And yes, that is true. Now, this is something that's above our pay grade, but I'm telling you for fun, because I got to keep this interesting for myself. It turns out that the #1 contribution to the opacity of the star, what makes all of these photons hit a brick wall, actually turns out to be H- ions. That is, occasionally,
Negative hydrogen ions.
yeah, so what would that be, Riker? What would that look like?
That would be the.
What is a negative? Okay, yeah, this is what they write.
So hold on. It would be a proton surrounded by multiple electrons.
How many?
At least 2.
2. That's right. Now, no, hydrogen normally does not like this scenario, but all things are capable in Professor Britton's wacky universe, and occasionally hydrogen atoms will temporarily grab onto an extra electron. Focus, focus, focus. And these extra electrons in the H- ions are so stupid good at absorbing photons that any photon that even enters the zone will instantly get absorbed by one of those H- ions. And that's what kicks off the convection zone. So in a way, the simple answer to why the sun transports energy, for radiation in the radiation zone and convection in the convection zone, is about the ratio of whether you're dealing with an entirely ionized plasma or a gas that has neutral gas atoms mixed into it. Now, okay, technically speaking, this is plasma. That's not neutral gas, but shut up. Who cares about that? All right, this is the concept. It's the basic idea. All right, so now you guys understand. Now, there was a reason why I took some time to explain those things to you, and that's because function F529. We are going to be studying other types of stars later today and next week, in which not all stars have the same relationships between their radiation zone and convection zone. There are massive, extremely hot stars that are almost entirely ionized plasma. And some of the coolest stars, like Betelgeuse, they have so much neutral gas that they're convective all the way down to their cores. So learning about the differences between these two layers is going to help build up a lot of intuition about how stars function. And eventually it will lead to cool things like why do they explode and go supernova. In any case, we've learned about these layers. It's time for us to plunge down into our favorite part of the star, and that is the nuclear core. This is the layer at which our temperatures rise to the key temperature of 15 million Kelvin, where hydrogen fusion can begin. Let's take some notes on this. Okay. So, in the center of the star, we arrive at the nuclear core. The temperature is a whopping 15 million Kelvin. In the core of the star, energy is not being transported, energy is being generated. And the energy generation method, of course, is nuclear fusion. Class, remind ourselves from last class, what is the difference between fusion and fission?
Fusion is combining the hydrogen atoms to build helium, and fission is splitting the atom.
Splitting a big fat atom, right?
Yeah, like uranium.
Exactly. Okay. Now, nuclear fusion can proceed by many different reactions, even inside the sun. But there is one reaction that dominates the nuclear fusion inside the sun, And the reaction goes by a special name. It's known as the proton-proton chain. And we are going to study the 3 steps of the proton-proton chain in some detail. It is sometimes unimaginatively referred to, I kid you not, as the pee-pee chain, okay? This is what people refer to it as. All right, so in order for us to understand the proton-proton chain, it might be first to imagine what it would look like if you could travel deep down inside and open up your supersonic microscope and look at the plasma particles inside the core of the star. Inside the core of the star, we have 3 protons traveling at extremely high kinetic energies, therefore very fast velocities, okay? Now, we also have 3 electrons swimming around in the pea soup, but the electrons are not exactly going to be involved in the nuclear reaction. That's not really true. Actually, the electrons are involved in a critical way, but for now, let's just say that the electrons aren't involved. What we're going to attempt to do is we're going to attempt to glue these 2 protons together. Now, 2 colliding protons, if you can give me a second here. 2 colliding protons are surrounded by an electrostatic barrier called the Coulomb field. And while these are technically magnets generating a magnetic field, it's quite similar in principle to what happens if you take 2 magnets and you arrange them so that their north poles are pointing towards each other, and you try to smush them together, and you feel that resistance of the magnetic field, and at the last moment they kind of push off to the side from one another, right? If I try to squeeze these guys together, they sort of push each other to the side. And imagine such a thing was happening with our 2 protons here. Occasionally, the protons, which are extremely dense, are going to fly towards one another, and their electric fields are just going to kind of push them side to side. And I'll draw that like so. One proton will get a deflection up and to the left. Another proton will get a deflection down and to the right. And depending on how fast and how hard you slam them together, there will be some minimum distance that they get between each other. This distance is called the impact parameter. And the name of the game in nuclear fusion is to fling these 2 protons at each other harder and faster at successively higher temperatures. And each time the temperature goes up, the distance between these particles, the impact parameter can get smaller and smaller and smaller. And at the key temperature of 15 million Kelvin, your impact parameter gets so small. Here I'm going to tell you a lie. Okay, I'm just going to lie to you because I like to lie to children. The particles can touch one another, okay? The impact parameter is so small that these 2 protons can touch one another. And when that happens, a new force of nature can take over. A new force of nature that is extremely powerful, but excessively short-ranged. I'm going to imagine it as some green Velcro that's kind of gluing these 2 protons together, okay? This is called the strong nuclear force.
All right, we started going over that.
Did we do that?
Kind of. We were doing it in some of our homework last Thursday.
I was kind of prepping you for that, right? So the strong nuclear force is stronger than the electrostatic barrier surrounding these protons, but it's very short-ranged. Gravity, electromagnetism, these forces can act over essentially infinite distances. But the strong nuclear force, which we do not fully understand, by the way, the strong nuclear force can only operate over distances comparable to an atomic nucleus. Now, nature will not allow you to glue 2 protons together just like that. That would piss nature off. So what nature is going to do is it's going to get one of these protons to eject its positivity-ness and transform itself from a proton into a neutron. you guys will recognize this particle here as a deuteron. That is the nucleus of deuterium, an isotope of hydrogen. This is called a deuteron. Nature will allow you to glue a neutron and a proton together. So part of the magic of nuclear physics is transforming this proton into a neutron by ejecting the positive charge. Nature is capable of doing this. Okay, now that we've had that kind of preamble, we can actually look at the 3 steps of the proton-proton chain. And I have them here in my slideshow, but it occurs to me that I have a slightly better cartoon to share with you guys. Let me do something here. Let me go to our lecture on stellar evolution. I keep forgetting to update my slides, but I eventually found a much cleaner information graphic that's going to help us to understand the 3 steps of the proton-proton chain better. Here we go. F573. Okay, we're about to do the 3 steps of the proton-proton chain. For the viewers later on who are watching the show, I'm just going to make myself a little box up here in the corner. Or maybe I'll go down here. There we go. Okay, so this cartoon shows us the 3 steps of the proton-proton chain. Step 1, step 2, step 3. And it's important that we take a look here at the total overall reaction of what's going to happen. We are going to take 4 protons, that is 4 hydrogen nuclei, or 4 protium nuclei, I should say. We are going to smush them all together and forge 1 helium nucleus. We're going to emit 2 gamma rays. Dog crew in the house. Okay, we're going to emit 2 gamma rays and a bunch of small subnuclear particles that I would like to talk to you guys about. So let's do these things as notes on our board. Let's see here. Stop share. There we go. Okay. 3 steps of the proton-proton chain. In the first step, let's see, can you guys see my slides okay here, or my notes? In step 1, a hydrogen nucleus, right, is going to slam into another hydrogen nucleus, and it's going to create a deuteron. It's also going to create 2 extra particles. One is something called a positron, and something called a neutrino. Now, because some of this chemical notation isn't so great for us, we're going to actually kind of draw this out below as a little cartoon picture. So a hydrogen ion is just a proton plus another proton are going to slam together to make our deuteron, which is a proton and a neutron combined. The positron is an antimatter particle that has the mass of an electron but is positively charged instead of negatively charged. So this little guy is a tiny little positive charge that has the same mass as an electron. And the neutrino is a uncharged particle, which is extremely, extremely low mass and very, very tiny. I'm going to represent the neutrino as a little microscopic dot. I want to take a moment to just talk to you guys about positrons and neutrinos, because when else would I ever get to do such a thing, okay? Now, you'll remember from an earlier part of our lecture that a proton and a neutron are kind of like big fat nuclear particles that each have a mass 2,000 times greater than an electron. So nature is weirdly asymmetrical about her design of nuclear particles, right? Protons and neutrons are almost the same mass. Electrons are much, well, I guess I could say smaller too. Their radii are smaller. But the charge of an electron balances out perfectly the positive charge of a proton. In 1931, maybe, a physicist like Paul Dirac suggested to his contemporaries in a paper or in a conference that perhaps nature was capable of reversing this asymmetry. Perhaps nature could create a big fat particle with a negative charge, which he called an antiproton, and perhaps nature was capable of creating a little tiny positive charge called a anti-electron or a positron. And he presented this paper at the, I don't know, the American Institute of Physics or some sort of conference in the 30s. And people laughed at him and said, dude, what the hell are you smoking? That's not how science works. You can't just make shit up. You can't just say, hey, wouldn't it be cool if nature just created these magical particles that no one's ever seen before? And then, of course, you know, 20 or 30 years later, they found all of them inside of massive particle accelerators, like the Large Hadron Collider. Do you guys know about this? You know about that Large Hadron Collider?
No.
I know it exists, but I don't know much about it.
Let's take a look at it. Because this is where, you know, some of our cutting edge nuclear research is done today.
That's where they make all the really heavy elements now, right?
You can make them in particle colliders, but the Large Hadron Collider has so much capability in terms of its energy that here that you're studying the very fundamental four forces of nature themselves. They can create energies comparable to, well, comparable to quite a bit. I'm not sure what I actually want to say there. Let's look at a picture. This is a reason why going into science is much cooler than studying art history. Sorry, art history majors. Why go to work in your boring office cube?
Wow.
Punch into work at the Death Star, right? So this is what you get to. This is your office, okay? If you are a nuclear physicist. Now,
a lot of shots here. That's crazy.
the way this thing works here is it's a 27-kilometer long track that spans the border between Switzerland and France. And the whole purpose of this thing is it's a big giant solenoid. It's a giant tube with a powerful coil of wires around it that generate an immense magnetic field. And they trap protons in the form of a plasma, and they just whip them around this track and spin them around until they approach speeds almost equal to the speed of light. So I think they can get particles accelerated up to like 99.99999% of the speed of light. They're almost going at the speed of light. And this gives the, oh, thanks for the helpful diagramming there, guys. This is great.
Well, the Large Hadron Collider is the one in the bottom left.
Oh, sorry. Thank you.
This is a future project.
The whole thing is, oh, this is a future collider. Sorry. Thank you. I was talking and I wasn't looking at my picture. Okay, fuck off, guys. What the hell? I think I can erase this. Oh, shoot. Anyways, by smashing these protons together, you do this and a whole zoo of subnuclear particles come out. In fact, one of the first ways that we used to identify antimatter particles is by, you may have seen this picture before, we study them in a bubble chamber, okay? Bubble chambers are kind of interesting because normally you can't really see an electron, you can't see a proton, and you certainly can't see some of these subnuclear particles. So let me walk you through this bubble chamber thing here because it's kind of a classic setup. I want just like a clean picture. All right, maybe this guy here. Okay, so what happens is they've got this goo, this chemical goo, where when ionized particles like protons or electrons fly through it, they ionize little particles of the goo and create these little tiny gas bubbles, which can be seen as tracks. So here, for instance, could be some sort of incoming proton, and the incoming proton is going to strike a particle and collide with it. And they suspend this goo in a potent magnetic field. And the magnetic field works so that If the particle has a positive charge, it'll gyrate and oscillate sort of up and to the left. If the particle has a negative charge, it'll spiral, let's see, clockwise down and to the right. So counterclockwise for a positive charge, clockwise for a negative charge. But depending upon the radius of these little oscillating loops, if the particle has a low mass, like an electron, it'll make a very big gyration. So you can tell this would be something like, this might be a positron. It might have a positive charge, but a very low mass because it makes a big gyro radius. And if the particles are massive, like the mass of a proton or a neutron, they have a much smaller gyro radius and they oscillate in smaller circles. So you can kind of quickly see whether you're dealing with a positive charge or a negative charge by studying the helicity, the counterclockwise or the clockwise nature. And then depending upon the radius of this oscillation, you can figure out the mass of the particles. What I'm trying to say here, guys, in some simple words is antimatter particles are real, and we create them inside of particle colliders all the time. Not only have we created antiprotons and anti-electrons, we've actually generated anti-hydrogen. We've actually created a temporary antimatter atom in which a big fat antiproton is being orbited by a tiny positron, and it actually makes a stable atom of antimatter. What's interesting, of course, about antimatter, and we probably should talk about this before we proceed further, is that antimatter, should it touch or collide with normal matter, will actually cause the particles to annihilate and sort of disappear and leave two small gamma rays in their wake that have the exact same energy as the particles. Let me see if I can find a cartoon slide of pair production or pair annihilation. There's one picture in particular, a nice little cartoon that I want to share with you guys. Here. Okay. So originally, people discovered about antimatter that should an electron and a positron collide with each other, they would sort of disappear from the space-time continuum, and they would sort of turn themselves into two very short wavelength, very high energy gamma rays. And if you measure the energy contained in these gamma rays, they are precisely equal to the rest mass energy contained in these two particles. Now, this to me is a very profound thing. If you think about it, positrons and electrons are matter. They are comprised of mass, kilograms, whatever the hell this mass thing is that we're talking about. And mass, of course, is a carrier of the gravitational force. When these particles transmute themselves into gamma rays, they have now become entirely electromagnetic structures, right? And these electromagnetic photons are entirely governed by the electromagnetic force. If ever there was a demonstration that there is a relationship between mass and gravity and electromagnetism, it's right here in this process we call pair annihilation. But to this day, there's a black box there. We don't fully understand how these particles can go from gravitational mass to electromagnetic energy.
So does that kind of like, you can't create or destroy matter? But doesn't that kind of contradict it?
Okay, it depends if you have an expansive view of matter or a limited view of matter. If you're thinking of matter as mass in kilograms, then you most certainly can destroy mass in kilograms, because here it's being converted into gamma rays. But of course, once Albert Einstein slapped us with E equals mc squared, it became no longer possible to talk about mass independent from energy, because the two are related. Today, we say there is a conservation of mass energy. So Nathan, if that was you that I was talking to, mass can be destroyed, but mass energy cannot be destroyed, right? So here, the particles have mass, and they have an equivalent energy, rest energy by E equals mc squared, and that energy is exactly equal to the two gamma rays.
Okay, thank you.
As far as I know, we've never been able to take a single particle of mass and convert a single particle into electromagnetic energy. There's the nuclear force or whatever is causing this, or I guess it's not the nuclear force, whatever mysterious process makes this happen, it can't do it for one particle alone. It needs a pair of particles. An even creepier version of the experiment, which was discovered later in the 60s, I believe, is where you took two gamma rays of exactly the same energy as a pair of electron and positrons, and you hit the two gamma rays together at just the right angle, and they will spontaneously turn into matter and generate two particles. This is called pair production. You know, after physicists discovered these reactions, reality just wasn't the same anymore. We used to think of the vacuum of space as just the nothing, the absolute nothing. And once we realized that particles could transform themselves from light into matter, people began seeing the vacuum as not necessarily pure emptiness, but a bubbling cauldron of primordial particles flitting in and out of existence. And that's some pretty crazy shit to think about, right? It's amazing to think that the vacuum of nothing isn't nothing anymore. It's a bubbling sea of virtual particles waiting to burst into existence. Some people believe, in fact, that the creation of the universe, the Big Bang itself, was some manifestation of a process like this, where a vacuum can suddenly burst apart into a sea of particles and antiparticles. And that, of course, raises some troubling questions, because we live in a universe that's dominated by normal positive matter with positive protons and negative electrons. But it almost seems to suggest that somewhere out there in the universe, there could be an overwhelming sea of antimatter particles that we have yet to discover. Perhaps there's even an antimatter Milky Way galaxy. Maybe there's an antimatter Earth with an antimatter you and me. And maybe that antimatter me pays his taxes on time. I don't know. Anything's possible.
This is why you don't smoke before science class.
Exactly.
Shots now, huh? All right.
Well, I have like a
Wow.
random question.
Juju.
Just in the information, all right?
Okay. We got one more. Look, I'm taking my time with this here and having some fun with y'all. But now you guys know about the positron. It's now time for us to talk about this little guy over here. This is the neutrino. So neutrinos play an increasingly big role in astronomy, and I want to tell you about some cool modern experiments in them, so bear with me. A neutrino, which is Italian for little tiny one, is probably one of the smallest low mass particles known to exist in nature. I usually represent it as a little tiny black dot. It has a very tiny, almost zero mass. And importantly, it has no charge. The fact that the neutrino is such a small microscopic bit of mass, and in particular, the fact that it has no charge, means neutrinos are much smaller than the spaces that exist between atoms. Neutrinos are capable of passing through normal matter as if it was transparent glass. In fact, despite the insanely high densities that you find at the core of a star, once created in the center of the star, neutrinos, unlike photons, can travel right through the radius of the star at the speed of light, as if the entire star was transparent. During the course of our lecture today, all of us sitting in our little homes will have neutrinos from the sun pass through the Earth and through our bodies in their journey through interstellar space. In fact, if you want to have a 100% probability of stopping a neutrino in its tracks, you need to have a slab of lead, and that slab of lead needs to be 1 light year in thickness. So a slab of lead that is 1 light year in thickness has a 100% chance of having a neutrino bop into one of those lead atoms. But if you only make your slab of lead a half a light year thick, there's a 50-50 chance that neutrino can pass through all of those lead atoms without striking a single nuclear particle. However, it is possible to capture them and to
Wait,
detect.
I have a question.
Okay, I want to hear it.
Is neutrinos another form of ray, like the ultraviolet, gamma, like how?
Technically speaking, no. Neutrinos are not electromagnetic. Sorry, let me say that again. Yeah, remember that gamma rays, UV rays, all that kind of stuff, those are electromagnetic photons. They are made up of electric fields and a magnetic field. Neutrinos, as far as we know, are actually made up of mass, which is gravitational in nature. So although, okay, you know what's kind of weird about photons? When you get down to the level of gamma rays are so short wavelength that in a sense they kind of act like particles themselves. Photons have wave-particle duality, so it's hard to answer that exactly, but I'll say this, no. You should think of photons as electromagnetic, and neutrinos are a tiny bit of mass, energy, okay? Now, I want to show you guys a couple of things just to kind of tickle your fancies here. For years, physicists searched in vain for a way to capture these neutrinos because they knew that if they could capture neutrinos, they would basically have a way to peer into the heart of the sun and directly observe the nuclear reactions happening there. Many people tried and failed, and eventually it was discovered, and I swear to God, you can't make this stuff up. Let me go to my lecture on the sun. That there was a chemical in commercial dry cleaning fluid, I kid you not, like the same dry cleaning chemical that you take your tweed suit to, and that this commercial dry cleaning fluid had a much higher than average probability of being struck by a neutrino. So they built the world's first neutrino observatory in South Dakota in a mine that was 2 miles underground. Here's a picture of it. They got a giant vat, a 4,000-liter vat of dry cleaning fluid, and lined the walls of the tank with these very, very sensitive photoreceptors. And they turned the lights off, and they sit there in the dark, and they waited for neutrinos to fly through space and bop into Mr. Clean here and create a little scintillation or a spark, which could then be detected by the photosensors on the walls of the cavity. And measure neutrinos they did. They collected neutrinos from the sun, and they found, for years, this was an outstanding problem in astronomy called the solar, oh, by the way, this was the first neutrino detector, the Homestake Solar Neutrino Mine. But people also discovered that, do you guys remember heavy water? Instead of H2O, it's deuterium stuck to water.
Yeah.
If you get a big vat of heavy water, neutrinos will strike the extra neutron a little bit extra as well. So they built another neutrino detector called Super Kamiokande in Japan. And here's a picture of Super Kamiokande. Here you can see the Japanese technicians in a little rubber raft. It's a huge vat of heavy water, D2O, of deuterium-laced water, and they fill the vat up. I don't remember what the volume of this is, but it's immense. You can tell by the size scale here. And they basically, these are all photosensors on the walls of the container, and they wait for neutrinos to come and hit the deuterium and spark a little spark. Now, what's especially strange is when they measured these neutrinos, they discovered that they were expecting to get something like, I don't know, 12 neutrinos per day from the sun, or 12 neutrinos per hour or something at Earth. And their initial measurements always got exactly 4 neutrinos per hour. They got exactly 1/3 of the neutrinos they were expecting. And this was known as the solar neutrino problem in astronomy for years. And it turned out that we believe we've solved this problem. It's kind of crazy. It turns out if you look at a picture of the standard model of physics, and this is where things get really weird. So smoke them if you got them, because it turns out there's not just one type of neutrino. It turns out that there are 3 different flavors of neutrinos. There are electron neutrinos, muon neutrinos, and tau neutrinos. And as neutrinos fly through space, the neutrino can oscillate its flavor and change itself from an electron neutrino to a muon neutrino to a tau neutrino. So one of the reasons why they always detected exactly 1/3 of the number of neutrinos they were expecting from the sun is because the Mr. Clean in the dry cleaning fluid could only capture electron neutrinos. But 2/3 of the time, the neutrinos were oscillating their flavor into muons or tau neutrinos. And this played a big role in us understanding how the four forces of nature are related to each other. This is on the very forefront of physics research today, trying to understand this giant diagram called the Standard Model of Physics. These are the wacky subnuclear particles that come out of those reactions that we study in the Large Hadron Collider. And they are related to the four forces of nature, and they are also related to how the Big Bang and the universe got its start itself. So there are some very big abstract questions connected to this diagram. Obviously, explaining the whole thing is more than I have time to do. It's over my pay grade. And egads, I've wasted a lot of damn time. Okay, so it occurs to me that I've almost out of time here because I've talked for what we're going to do is we're going to finish our 3 steps of the proton-proton chain. I'm going to show you some radioactive shit, and then we're going to do our homework, all right? So let's finish our notes. Okay. In first step of the proton-proton chain, a hydrogen plus a hydrogen creates, here are the symbols I'm going to use. A deuteron is a D with a positive plus there. A positron is a little e for an electron, but with a positive charge next to it. And the symbol for neutrinos are the Greek letter mu. It kind of looks like a V with some cool curves to it, all right? In step 2 of the proton-proton chain, our newly formed deuteron is going to slam into another free proton, another hydrogen atom, and it's going to form an isotope called helium-3. I guess there's 2 charges there. I'm going to omit the positive charge. So there's helium-3, and it produces a gamma ray. Step 2 of the proton-proton chain is critical because this is where all of the energy of sunlight comes from. So you can think of step 2 as where sunlight is born. And in order for step 3 to happen, step 1 and 2 have to happen twice. And our helium-3 ion collides with another newly formed helium-3 ion to create a proper helium-4 nucleus, and it leaves 2 leftover protons or 2 leftover hydrogens as a byproduct. Now, I also want you guys to write down the net reaction, and then I'm going to show you the picture of it here, okay? The net reaction is 4 hydrogens combined to create 1 helium and 2 gamma ray photons. And this is how hydrogen is transmuted into helium in the sun and releases energy in the form of 2 little gamma rays. These gamma rays will then wiggle and random walk their way through the interior of the star on their way to the surface of the sun, where they can shine themselves into space. Now, I want to show that to you guys in cartoon form because I believe that some of those symbols can be kind of alienating and not germane to the average human. So F573, here's the picture process here. 2 protons collide to make a deuteron. They emit a positron and a neutrino. The positron will collide with a free electron somewhere in the star of the sun, and they'll annihilate and create some gamma rays. Forget about those gamma rays. They're not part of the reaction. Then the free deuteron collides with another proton to make helium-3 and emits the gamma ray. That's part of the reaction that creates sunlight. Then our 2 helium-3 particles, this one was formed by step 1 and step 2 somewhere else, will then combine to make a proper helium nucleus, 2 protons and 2 neutrons, and 2 protons are released from the reaction. Now, a pesky student might ask me, hey, Brendan, didn't this positron go through an annihilation with an electron? And didn't it create 2 extra gamma rays? Shouldn't that be some extra energy that the sun produces? And the answer to that question is weirdly no. It's no because of the way in which a neutron is formed. In order to generate a neutron, in order to generate, well, I don't know if I want to get into all that because of time constraints, but basically, let me go off my to my screen here for a second. In order to transform a proton into a neutron, you actually have to take a proton and you have to create an extra electron inside the sun by a pair creation process where 2 gamma rays collide to make a positron and an electron. They also create a neutrino and an antineutrino. And then the electron, the antineutrino, and the proton all smush together to make a neutron. I only mention this because the process of pair creation is also happening inside the sun. They just didn't show us in that portion of the lecture. I like your background jams here. Okay. Well, look, we've wasted another day talking about nuclear reactions inside the sun. And I hope you enjoyed it. Let me look at the time. I think maybe I'm going to save my radioactivity demo for next time because we've got some homework to do. I know that, that you guys have other stuff that you need to do in your lives. So are there any, by the way, our homework today is the homework on chapter 15. So we haven't quite gotten there yet, but the problems are very simple. So I think we're just going to crash our way through the sample problems. Does anyone have any questions they want to ask before we stop the lecture portion of today's class?
Well, for the homework, right? I guess I'm going to find out right now. So like we go into Blackboard, or do you just like open up a folder?
Sure. Let me show you what to do. Today's homework is going to be a little awkward because my lectures have dragged behind where we should be homework-wise. I could make up new problems for us to do, but I think I'd rather just kind of go with the program.
I don't want to make problems with this topic. It's a hassle.
That's right. I don't want any problems with my problems. So can you see my screen there, Juju, or whoever asked that question?
Yeah, I can see it. I can see it.
So if this is your astronomy, oh, this is 1010, the solar system. Hold on. You
Lame.
guys, yeah, not cool. Go to astronomy 1020, spring 2020. Go to homework. And this is what we're doing today. We're doing chapter 5, problems, chapter 15, excuse me, 45, 54, 55, 56, and 57.
Oh, wait. So we're going to do so right now we're going to do it like together and then just later on go on there and input the.
Yep.
Okay.
Can I recommend something, Juju? I'm going to walk you through these problems and basically solve them all for you. So why don't you just copy everything that we're about to do and then submit that?
Yeah, that's what I'm saying. I'm saying that's probably what you.
Yeah, that's what I just
we do it together. So
Right,
I
Carl.
thought that was gonna work, but now I realized that so you're gonna do it now and then later on just input it into the Blackboard and then that's
Yeah, and after that you can submit it.
Riker also has a habit of typing everything and then throwing it into the chat.
Yeah.
So
actually,
I don't just grab it from there.
I don't think there are almost no word problems today. They're all simple math problems with maybe one sentence or two at best.
Riker,
yes, that is so rare today.
Riker, we could still use your help, okay?
No,
Riker,
do it
anyway.
Just get out of here.
Yo, Riker, I might need your number. I'm not gonna lie.
Look,
Juju, you got a Discord?
Huh?
Do you have a Discord?
Nah, I don't.
We have a Discord.
Yeah, these guys have some kind of a Discord file sharing service, so you guys can
Is this something I can like?
Look, I'm
Download
gonna
on
give
your
you guys the answers
Yeah, it's
anyway.
an
Yeah,
app.
it's free.
Yeah. No, but that's just for the ones that I missed. That's how I need like to see if you can help me out.
I can send it to you.
Okay. Just, I'll collect your number later. Let's just focus on this now.
All right,
Yeah,
look,
got you.
Yeah.